For decades, several programs have been developed to verify mathematical proofs using computers. Today, the most notable are Coq and LEAN. However, they are focused on checking proofs and have paid little attention to the potential pedagogical value of a verified proof. We believe that the importance of a verified proof lies in how much it can help others understand it. Mathdialog, as an interactive theorem prover, is the tangible result of that idea. In Mathdialog's terminology, the proofs we communicate to it are called human-to-machine proofs. These proofs are saved in a formal structure that is neither natural nor pedagogical, making them difficult to understand. To address this problem, Mathdialog automatically transforms proofs from their formal structure to a form that has straightforward ways for users to find answers to typical proof questions such as: what is the definition of this predicate? Where does the justification for this hypothesis come from? What is the justification for this step? What does the theorem that justifies that hypothesis state? And what is the definition of this term? The proofs in this format are called machine-to-human proofs, and they are the kind you can consult right now at mathdialog.com. In the first part of this video, I will show what it feels like to consult proofs by going into the machine-to-human proof of INV group uniqueness, which says the inverse in a group is unique. This is interesting because it will allow us to show the versatility of machine-to-human proofs as a bridge between natural and formal mathematics. In the second part, I will show how easily that proof was built using its corresponding human-to-machine proof. First, we start Mathdialog. From these menus, we choose Theorem by name. We write the first letters of the name we want in group uniqueness and click on the Send Theorem Name button. We double-click on the theorem's name in the list, and we get the theorem. In this video, we will navigate by the consulting machine-to-human proof's main steps. You can consult it on mathdialog.com for a deeper navigation. To start the interactive proof, we navigate the menus and choose Proof of. In the goal window is the theorem's thesis. The theorem's hypothesis is the first one in the hypothesis window. The second hypothesis is the result of the first step of the proof. In the step window is the explanation of the first step, the application of the group direct zero theorem. To consult what it says, we double-click on that name to select it and select the selected name from the consult menu. Then, we select group to see its definition. Now we can see why it is a direct consequence of the group's definition. We click the forward button to go to the next step. The step window says the third hypothesis is obtained by instantiating the variable x prime. If we need further explanation, we can click on the step explanation button. We go to the next step. The step window says it has proven the formula in the goal window by proving the three formulas shown. The fourth and fifth hypotheses are not interesting because they are already in our hypotheses. To see the proof of the sixth one, we click on it. The clicked hypothesis becomes the new formula in the goal window, and the fifth hypothesis is now the result of this step by equality. The next step is the application of another theorem. But because we see that the formula in the goal window is a consequence of our hypotheses, we click on the I get it button to finish the subproof. But before, let me show you that at any time we can get the justification of all our hypotheses by clicking on them. We return to the step we were at before we started the subproof. Now we are sure all conditions to prove the uniqueness existential quantifier are satisfied. So we consider our goal proven and finish our proof. Clicking forward, we exit our machine-to-human proof. Now we will use a server that does not know the inverse group uniqueness theorem to build the human-to-machine proof that Mathdialog used to generate the machine-to-human proof we have consulted. In contrast to the latter, the former requires knowledge of Mathdialog, but we will see it is intuitive, easy, and natural. In Mathdialog, you build a proof by interacting with a dynamic and hierarchical list of hypotheses and goals called a proof list located in the blackboard. The user writes logic commands in the command window and sends it to be processed by the Mathdialog server. It responds by adding new hypotheses and / or a new goal to the proof list. To start a proof, we write a theorem in the command window. Theorems in Mathdialog must have a name, a list of atomic formulas that are their hypotheses and their thesis. G is belongs to, and T exclamation mark is the existential quantifier of uniqueness. Now we click the send command button to start the proof. The theorem's thesis is the first element of the proof list marked as a goal with GL, and its hypotheses are marked with H. We know that in a group, by definition, each element has an inverse. The by theorem logic command has a formula as an argument. If it knows a theorem that has that formula as its thesis and its hypotheses are in the proof list, Mathdialog adds that formula to the proof list as a new hypothesis. Mathdialog adds the logic command to the proof list with the U, then the hypothesis it generated. Now we need to instantiate that new existential quantifier in our hypothesis with a new variable. Existential quantifier reduction from hypothesis as an existential quantifier formula and a variable as arguments. It checks if its first argument is in the proof list as hypothesis and that the variable is new. As before, it adds the logic command and its result, the instantiated formula, to the proof list as hypothesis. Now we have S' as a candidate for the uniqueness quantifier in the goal. Existential quantifier reduction logic command has a variable as an argument. It checks that the goal is an existential quantifier and that the variable is present in the proof list. It adds the logic command, but instead of a hypothesis, it adds a new goal to proof list. It will successively ask for the scope of the former goal, its main formula, and finally the uniqueness part. Propositional consequence checks if its argument is a propositional consequence of the hypotheses in the proof list. In this case, it is the way to tell it that the new goal is in the proof list as a hypothesis. Now it is asking for the main quantifier formula by putting it in the proof list as a goal, but it is also there as hypothesis. Now it is asking for the uniqueness part. It chooses a new variable and put the equality as the new goal, adding these hypotheses. If we prove the equality, it will consider the uniqueness existential quantifier main goal proven. Equal equivalence checks if the equality in its arguments is a consequence of the equalities in the proof list hypotheses. We use the by theorem logic command again. Now the equality goal formula is a propositional consequence of the hypotheses in the proof list. QD. The formal Mathdialog proof is this list of 8 logic commands. And the most important remark is that from it, Mathdialog builds automatically the interactive proof shown at the beginning of this video.